Okay. Oh, wait. Almost. Okay. Okay, we should start. So today we have special guests here. So I might have to address them every now and then. Sorry about that. But they contributed data to our last lecture, so that's I think that's a fair price to pay. Good. So today I remember to share the slides online, so everything will be copacetic. Before we start on exactly what we're going to talk about today, I just had an addendum on the pizza example because I realized I didn't bring an important point home. So if you remember, right, we had predictions from the model for the 3 different raters. And we were discussing that the quality of the data might be a bit varying between the raters, but also that there are structural characteristics that are different between rater N and rater R. Right. And last week, I simply said that, well, that means that we can learn something about the model and the word, because rater N was measuring the heat at the boundary between the flame and the stone, and that reflects the assumptions of the model better, right? Because the model assumes, in the simplified form that we use to be able to fit it to the data, assumes that the heat transmits instantaneously. While when somebody is measuring it in the middle of the baking stone as rater R, that takes a while for the heat to reach there, right? However, right, we don't just learn something, right? So these things have implications for the decisions that we need to make, right? And that's very important. To quote a title of a book that I recommended last week, right? We need to escape model land at a certain point, and we need to make decisions in the real world. So what is the implication of this pattern that we just learned of the limits and possibilities of the model for our decision on how long to wait until we can put a pizza in the oven? Yes.
Well, the stone is not heating uniformly.
Yes.
So I guess the model doesn't completely reflect.
Exactly. And then how would we make decisions accordingly, right? How do we escape? Because the model, it's telling us, well, if you want to reach 400 degrees or whatever you need to wait, let's say, 17 minutes. Can we trust the model? Yes, Martin?
So we can set the value of how much we're going to wait based on our preferences about whether it would be okay for us to wait a bit longer, or if it's better if we don't waste energy on heating up the stove more than it needs to be.
So we're an Italian household, so the word can burn as long as we get good pizza, right? Not true, but yes. So, okay. So basically what this is telling us is that the pizza has to bake all the way through, right? And the center of the stone is very important. The center of the stone is lagging behind according to what the model is telling us. That means that if we want to make a good decision in terms of pizzas and dam with the planet, right, we got to wait a bit longer. So by understanding our model, we can actually also adjust the concrete decision that we can make from the model. Yes, that's exactly. So we can add 3 to 5 minutes to the model estimate. And I think that this is very important because it brings home the point that really trying to understand your model, that really trying to, I think this is called retrodict. So for instance, compare the predictions of the model with the real data gives you actionable insights. So we're not going to spend the next 11 weeks just nitty-picking about, does this model work? What if we predict the data in this way? What if we look at the data in this other way? It's not just because this is a course about models and we're going to nerd 100%, but it's actually because knowing where the model works and where it doesn't, it gives us actionable insights. Good. Questions? Yes. I actually have a quick question. Have you checked the course notes?
You mean the GitHub work thing?
Yes. Any comments on that? Are they helpful? Because I rewrite them every year, so any feedback helps me sort of adjust the trajectory. Right. Of course, now there's no code. Well, there was code for the pizza, but it was not something that you need to be able to use at this stage. But if you have comments and things, just let me know. And it's actually quite important that you spend a bit of time going through the course note at some point after the lecture so that you sort of consolidate what has been covered. And sometimes there's a bit of complementary things because it depends on which trajectory the lecture has taken. Good. So what are we going to do? Last week, we did an introduction to cognitive modeling, and we discussed potential cognitive models underlying the matching pennies game. This week, we're going to do a brief recap. We're going to then spend the bulk of today on how do we formalize generative models of cognitive agents. For some of you, it's going to be pointless programming recap, but we're going to go through the step because it also consolidates the conceptual parts of building models of agents. And then what we're going to do next week is we're actually going to zoom out, take a more complex model than what we're building today, and then wrap up both a forward modeling and an inferential modeling of that. Might be, I think I have slides for win-stay-lose shift, but I think that time allowing, I'll actually go full in a reinforcement learning agent because it's more fun. Okay, so what did we learn? Key ideas: cognitive processes underlie behaviors, and we can formalize these processes, for instance, learning, for instance, biases, to make better sense of behavior and compare and develop the models. And we anticipated that there are structured workflows to make formalization manageable, transparent, and stress test. And we're going to develop that through the next 3 to 4 weeks. By formalizing the models, you put your thoughts, science out there, you open it to critiques and falsification and community development, which is something that verbal theory is also allowed to do, but in a different way. Right? It's always possible to discuss the meaning of words, but if there is a parameter with an exponential decay, there's not much arguing about what's the underlying conceptual model of forgetting. I think I'm going to skip this because where I want to spend a bit more time is that we discussed some models last time that are actually related to each other. And I didn't spend enough time discussing that. So we discussed about memory as, actually, there. So we discussed different models on how we can keep track of how our opponent is playing the matching pennies game. And one was the moving average. Actually, the first one was simply an average of what the other is doing. If we consider right being 1 and left being 0, we can sort of run an average, and that's our propensity to pick right. Then we have a moving average, which allows us to include some very rudimentary model of forgetting, right? How memory actually works. But we also discussed that memory doesn't work in chunks, but it actually has an exponential decay. We discussed a few ways of formalizing that. And at a certain point, maybe a bit cryptically, I said that the reinforcement learning is what helps us modeling decay in a nice and mathematically elegant way. We also mentioned very briefly that another way of calculating or thinking of how our estimate of the other's propensity to pick right could be formalized using a Bayesian update. And then I didn't mention that there's a couple of other models out there that you probably met, but if not, we can very briefly discuss them, that seem to be doing the same thing. So I'm going to go by step through them, right? So we can actually see how we can think through our memory constraints through existing models, but also how to try to bring the existing models under a common framework that allows us to think more critically about them. And so if we look at the average, that's kind of, so we do the sum of whatever the choice is, and we divided it by n, how many choices there have been so far. If we do a moving average, what we do is simply I can't remember how I didn't formalize it there. So we basically use the same thing, but we say, oh, we're going to use 7 choices, right? If we move on to the reinforcement learning, what we're doing is we're implementing a very specific way of thinking about memory and learning. So we have that our expectation of the reward, whether we win or not, in picking right, depends on our previously expected value, which could be simply the mean. Right? But this value gets updated according to a very specific formula, which is alpha times the predictive error. What is the predictive error? Is the feedback minus the choice, right? We make a choice, not minus the choice, stupid, me, minus v at t minus 1, right? So our expectation clashes potentially with the feedback. The bigger the clash, the more we change our expectation for the next round. Does that make sense? However, we have a moderation parameter in this process, which tells us how much should we learn on any given trial. Should we be skeptic? And then we would have, I don't know, a learning rate of 0.1, or should we be very eager? And then we would go all the way in, right? So we take at face value the clash between our expectation and the word, and we bring that back to our next round of expectation. Right? And these model by default implements, again, we're going to go through the math of that next lecture, so I have an actual slide on that. But these model moving, since alpha moves between 0 and 1, by default elegantly implements the exponential decay, right? Because the impact of whatever happened before gets weighted down. Let's say that what happened at this round only becomes 90, it only weights 90% on our change of expectation. As we get to the next round, not only the new part gets down weighted, but also everything that happened before gets down weighted. So if you multiply 0.9 by 0.9 by 0.9 by 0.9, you get an exponential decay. And the shape and speed of the exponential decay depends on the value. If you multiply 0.1 by 0.1 by 0.1, the exponential decay is much faster than if you have actually, it's the contrary. So 0.1 by 0.1, the exponential decay is slower than if you have 0.9 by 0.9. Another way of thinking of these updates is using Bayes, right? And we'll do that in depth when we get to those kind of models. But the basic idea of Bayes is that we don't just have point estimates of what we expect, because according to the experience that we had of the word, you remember from the McAreath book, right? As we go through these, what was in the marbles from the factory, right? If we seen, okay, let's go here. If we seen one of you picking right and then picking left, this is a 0.5, this is 0, this is 0.1, we're gonna have a pretty broad distribution of what the possible underlying rate is. But if we played with this person 1,000 times and they had picked half of the times right and half of the time left, we're going to have a very pointy distribution at 0.5. These will impact how much we're going to change our idea as we encounter a new trial. In the first case, right, with a very broad distribution, just one more data point can skew our new expectation very strongly, right? It's going to move it a lot. But after having seen 1,000 trials, 500 right and 500 left, just seeing a new one is not really going to change our expectation. Does that make sense? If we want to formalize that formula using reinforcement learning, what we say is that the parameter that there is the learning rate, which is fixed, where we always trust the word at a given level, right? If it's very noisy, we trust it little. If it's very reliable, we trust it a lot, but that value is fixed. Here, that alpha is replaced by the squared variance of my expectation, the uncertainty of my expectation, right? Divided the uncertainty of my expectation plus the uncertainty of the signal that's coming in. Yes.
Couldn't we model this just like a zero update to beta binomial for respect to log?
So yes, it's equivalent. But we're actually going to do that in the third assignment. But this is just to say that what we'll see as a Bayesian update, and you've seen formulas of Bayesian updates in methods 4, can actually be brought back to the same formula that we have here, but the learning rate is a function of the uncertainty in the prior and in the likelihood, if you want. And it can be formulated in different ways, but this is a way of making it along the same framework. Yes?
I think I need to be handled to prove this.
Yes.
So if the uncertainty in the prior is high,
Yes.
then that happens to the learning rate.
So the learning rate, so if the uncertainty is very high, what we have is that, and the uncertainty in the signal is very low.
Yeah.
We have that it's the learning rate should be very high. So I don't know, 0.9 divided 1 is going to be pretty high. It's going to be still 0.9. If the uncertainty in the signal increases, right, it's going to be 0.9 divided 1.3, right? So the learning rate decreases.
Yes.
So it's not as much about the absolute value of the uncertainty in the prior, but it's in the relation between the two. Yeah. Good. Have you met Kalman filters? Not decision making, that wasn't covered, right? No. Okay. Kalman filter is a very popular equation in engineering, which basically is saying that the uncertainty of the word is not a fixed data point. So here we sort of relaxed our assumption on how much internally uncertain we are, so that as we learn more and become less uncertain, potentially, we learn less from the word. We don't let ourselves to be swayed as much from the word. That's called getting old. Here, we also say that we assume that the rate of the word outside can actually be changing. And so we adjust the learning rate not only on our internal uncertainty, but also on whether the word is stable or not. And it's called the Kalman gain. We're not going to go right now through the equation, but just to give you an idea that there are these models that sort of take different components and open them up. And if you look at the Wikipedia page, it's going to have a very different equation, but you can actually reduce it to this formula where the learning rate is adjusted to how much the word outside is changing. Have you been exposed? Yes?
Just the Bayesian update again,
Yes.
because I think I'm a bit.
We're going to go through that in detail, right? So this is, again,
Should if we are very uncertain,
yeah.
shouldn't that correspond to a high learning rate? Because we then skew our expected value.
So of course it needs to be in relation to the uncertainty of the word, right? So those two things go together. Because if you have a high internal uncertainty and a high external uncertainty, then you're not going to move your expectation that much, right?
But what does the external uncertainty? Maybe that's what I don't get. What that
Yeah.
is.
So it could be that I can remember somebody last time was maybe playing 5 times right, and then they would be playing random, and then they would be playing 10 times left. And if you just take the standard deviation of the signal that you get in a given window, it's going to be very different. It's going to be very low when they're playing consistently, and it's going to be very high when they're playing randomly.
Yeah.
Yeah. Exactly. And good for questions, right? This is great. Yes?
So the context that I have the Kalman filter, it's like a late rainbow model where there's Gaussian random walk in late space, but there's a Gaussian output. I just
Yes.
have to relate that to this.
You just put binomial at the end. You can do the same thing.
Late state is not.
Yes, exactly, because it's a rate at which right can happen in the other behavior. So it's not the 1 or 0, it's not the left or right, it's the rate at which we expect them to pick right.
Okay.
So what he's saying is basically we have an internal model of the word, which has a mu, which is an expected rate of the other, and also has a sigma, a standard deviation. And as we play against our opponent, we don't just update the mu, we also update the sigma. So that if the word becomes more messy, we're gonna update less. If the word becomes more deterministic, we're gonna update more. Now, this is just a kind of a wink to Chris Mattis, who's in our department. I don't know if you had him, but his whole career has been building this model called hierarchical Gaussian filter as a model of how the brain works. And the hierarchical Gaussian filter is nothing but exactly this sort of progression, but we add layers. So we're saying that sigma is not just a distribution, or it's not just a point estimate, but it's a distribution where we have a mean and we have a variance. And mu is the same. What does this mean? It means that we don't just adjust to the uncertainty of the word outside, but we actually try to estimate how fast the word is changing. So we have an expectation that the word might be changing at different levels. And then we can go one level further. I think it goes up beyond that, but I think that the third level is the only level I can make work in simulations, then it stops working for me. But the other is how fast should I change my expectation of how fast the word is changing, right? Think about climate change, right? So we have a certain expectation that the word changes because there are seasons, but with climate changes, the changes are becoming less stable. So we need to include a higher uncertainty, a higher variance in our expectation. And this higher variance in our expectation has to increase over time because climate change is creating more bigger and bigger feedback loops, right? Yes?
Related to the K patient,
Yes.
I think I have like a little bit of why sigma noise is sigma. Instead of the sigma.
Sigma is the uncertainty. So sigma noise is the uncertainty in the signal that's coming in. Yes. So think in Bayes, you have the prior and you have the likelihood, and you use that to generate the posterior. How much the posterior deviates from the prior depends on how uncertain the prior is and how uncertain the likelihood is, right? So how uncertain your internal expectation is and how noisy is the signal. Where noise is simply variance, right? Yeah. It doesn't have any ontological implication. Good. So I put everything here in the slide, but I just want to get you used to the kind of thinking that we're going to do through the course, right? Okay. I'm actually gonna skip this because we can start. It's more fun. And the way that I'm gonna present this, I've been debating last night whether I should turn it all into a live coding session, but I haven't because I had to get up at a certain hour this morning. But I'm gonna show you some basic ways of coding agents. And as I said, for some of you, it might be too basic. And we'll discuss the conceptual steps in that. So the assignment that you have to submit by next week is that you have to create a document and a GitHub repository. And in a sense, what we're doing today is we're going step by step through the things you have to put in the GitHub repository, right? Two possible strategies to play the matching game include a discussion as to whether include cognitive constraints, for instance, memory limits, blah, 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 or executive functions, so errors and the like, report the formalization of these strategies, and include plots. You need to separate the report and the GitHub repository. Good. So, okay, we've done that last time. I'm not going to redo it now. So as we go and start formalizing the matching pennies game, in this specific way of thinking about our task, we're going to start from the task. Right? We'll have future assignments where we start from the theory, and then we adjust that to the task. Here, we start from the task. You've gone through that. You were playing against one of your mates. And so what does an agent need on a turn-by-turn base as input to play the matching pennies game? Yes? Oh, actually, I'm just thinking very basically in terms of you need to make a decision, right? What do you need as input? Yeah. So for instance, what the other person has just done. I'm not going to say memory, because if we want memory, we might want to have it internal to the agent, right? To be consistent with the conceptual framework.
Like if you have bias.
Yep.
You want to just give it a possibility when it runs. And each time you can upload.
Yes, good. So, right, if we take it very basically before we go inside, we need an input, which could be their own previous choice, depending on the strategy, right? The opponent's previous choice, the feedback, whether they got it right or not. Those three, of course, can be reduced to two, right? You just pick any two of them and you get the third for free. Then we need, as you were saying, and remind me of your name, Peter, yes, thanks, is an internal mechanism that turns the input into a prediction of what to play. And then we need a decision mechanism turning the prediction into a choice. And this is something that's actually quite crucial. We separate the internal estimation, sometimes it's called, from the decision rule. I'm sure you've done that in decision making as well, right? Right. We want to first estimate what's the probability that the other will play right, or said in other words, what's the expected reward for us in picking the right hand, from what then we do with these information, with this estimation. And then from the decision, we extract an output, the choice. These, if you've done any programming, right, can actually be turned into something that you know pretty well, which is a function. Why are we doing functions and not objects? I don't know. I find them more intuitive for these sort of things, but you can use objects if you want. So pseudocode tells us that there is an agent function which gets some input and some parameter values, and it produces an output. So if we pick, right, a biased agent or random agent, we can define it as this is the random agent function, which is a function which takes this input. And tell me if I'm going too slow, but every year there is always somebody who's not feeling very confident in programming, so I've sort of developed the slides to go step by step. Following on what we have been discussing, right? What we have is that a random agent, so an agent that has, let's say, an 80% chances of picking right, will have some input. But really what matters for that agent is the rate at which they pick right. Then we have an internal mechanism, which is only a decision, because this agent is not really doing anything with the input, right? It's completely oblivious to what the other is doing. So the decision making is a binomial sampling. It samples one time, right? For one trial, because we're running one at a time. And the rate at which it picks right is the rate that we fed to the agent. And then we return the choice. We produce the behavior. Is this all clear? Good. So what we can do in this specific case is then we can remove the input because we're not using. Sometimes we keep it for consistency, so we have all the agents that get the same input, which simplifies the programming. But for the rest of the slides, I'm going to remove it because it's saves space and it's easier. Okay. So what is this agent doing? We give it a rate, theta, or bias. It's called in many ways. I'll try to keep constant and use rate, both in the course notes and here. After many, many complaints that I was keeping and shifting things between channels. So we have that random choice is the produce of the random agent function with the rate that we just defined. And then we can display it. So now I'm going to run it for 120 trials. I'm going to create a vector, empty vector of length trials with just NAs as choices. And then I'm going to say that for the sequence of trials, so I'm going to say for a variable called t, which goes through the values that are generated by the sequence of trials, so from 1 to the trials n, the random choice of time t is given by the output of the random agent with a rate of rate. Then I make these into a table because I like to work in ggplot and the tidyverse, where we have the trial is the sequence of trials and the choice is the random choice. And then I create a ggplot that takes the D1 table that we just created. It visualizes on the x-axis the trial, on the y-axis the choice. It runs a line between these points, and it uses theme classic because I hate the gray background. And then we display the plot. This is telling us how erratic the agent is, right, when it has a rate of 0.5. This is very basic, but ask questions, right? I'm just setting up the foundations. What about different rates, right? This is where programming is helpful. And again, this model is stupid, but we set up the workflow so that when we have complex models, we can follow the same procedure. So we ensure that the data frame or the table is empty, and then we can say that looping through the sequence of rates that go from 0 to 1 in steps of 0.1. Right. We create an empty random choice vector of length trial filled with NAs. Then we loop through all the trials and we fill in the vector for that very specific rate, right? Then we create a temporary temp table where trial is the sequence of trial and choice is the random choice. And then we say rate. And then we say that if D1 exists, we just append temp to D1. Otherwise, we just create D1. So we're looping through rates, and within each rate, we loop through the trials. Again, there's more elegant ways of doing this since the agents are stupid. They're not using the input, but we follow the loop because it does things step by steps. And then we plot it. And the only thing that we change is that we facet wrap by rate. So we make one panel for each rate. Right. So even if we have very random agents, right? So there's a lot of stochasticity, we can already see some patterns here. What are the patterns that you see? Yes. Yeah, you since.
Sure.
Yeah.
Okay. Well, as the rate increases, it's more likely that they won't.
Yes.
Yeah.
Exactly. And so you can see that they stay longer up, right? And they go fewer times down. Right. Is it very easy to see differences in the middle row? No. And part of that it's because it's random. Part of that it's maybe because our representation is crap. Right? So always question the format in which you're representing the data. So how would you represent it better? Yes?
Maybe you could have like two bars next to each other. Choice.
Yeah, I think that this is not a bad idea, but it forgets time, right? And time is quite important. Yes, Martin?
Like black and white bars.
Mm-hmm.
instead of the line going up and down. So there would be a white bar when it's 1 and the black bar if it's 0. Yeah, and then it would just read like line code.
Okay, yeah, like some sort of barcode. Yeah, cool. Yeah, that's not the solution I had in the next slide, but that's a good one. Any other guesses or takes? Yes? Yeah, so we can do a cumulative rate. Yes. Does that make sense? Right? It tells us of the previous whatever trials there have been, how many have been right. And then we can see how that oscillates. So we calculate the cumulative rate. So we say sequence along choice. So in the first trial, it's 1. In the second is 2. In the third is so far, blah, blah. And then we do the cumulative sum so that every round, every trial, we add whatever is in that trial. And I know that's a very bad pipe. It should be the new R pipe. I didn't get around to fix the course notes, and then I didn't fix this. Then we do the plot as before. Trial is on the x-axis, cumulative rate is on the y-axis. We use a geom line. And then we add, just for reference, a line at 0.5. And then we can see how at different rates, right, we converge over the actual rate of the model, right? So that in the first one, we stay at 0. At 0.1, it oscillates briefly at the beginning, and then it goes at 0.1. And at 0.2, it oscillates, in this very specific case, more. And then it goes at 0.2 and 3, and so on and so forth. And again, these might not be the best way of representing it, but we can put all of them in one plot. And then we get a better idea as to not only the fact that they take time to show their underlying rate, but also that if we take a shorter N of trials and only one agent, it's very tricky to disentangle their behavior, right? So there's a lot of overlap here at the beginning. You should probably note also something else, right? Is there something qualitatively different between lines from rates of different values? Yes, Martin?
They kind of stay more like a method walk. We don't have these huge sweeps.
Yes. So if the farther we go from the center, the more deterministic or the less variant the lines are. The more we go towards the center, the more the swing. Right. Which tells us something important, that also depending on the behavior of our agents and of our opponents, some of them might be easier to infer, others might be harder to infer. Right? Okay, and that again might not be the one only representation that you want to have. So here I did something else. I ran that loop before 1,000 times so that I can actually show you the variance for each rate. So what you can see here is darker lines, which are the mean across the mean of the cumulative rate across the 1,000 agents. And you can see they're basically straight line, right? There's something off at the beginning, but they converge extremely rapidly. But we can visualize perhaps better the variance or uncertainty across the single agents with that rate. And then again, because I'm never happy, I also represented that variance by rate over the trial number. Right? So that tells us how quickly the variance goes down between agents. Do you notice anything in that? Somebody else? It's a subtle point. It's not really a big conceptual point. Martin?
Looks like one of the racks.
Yes, it is. It's an exponential decay. Yes, great. There's also something else, which is they're symmetric. So you actually see only half of the lines here because 0.9 and 0.1 have exactly the same variance. 0.8 and 0.2 have exactly the same variance. So if you're exploring your model in this specific case, you could simplify your simulation and only go for half of them, right? And then I'm just going to show very briefly before the break another way of simulating this. And I need to share in a different ways. I don't, how do I do it? Just entire screen. And that's something that I've been starting to explore on how to visualize these things, which I think is pretty neat, where you can actually make a shiny app that allows you to say, oh, I'm only looking at 10 trials. And then it shows you the plot. And then you can change and say, oh, I only want 50 agents and see how the uncertainty changes. And that's, again, something that I find very useful to explore models. And with that, I'll and share. Okay, we'll start again. Just a quick note on the formulas. I know I went a bit fast through them. I just wanted to give you the basic conceptual understanding. As you see now, we changed the pace, right? We're going very slow, step by step. So when we get back to those formulas, then we'll also keep these pace. I was also sharing with somebody before that in 2011, 12, when I looked at these equations, my eyes would glaze over and move to the text. So that's actually something that's absolutely understandable as a reaction. It just takes, for me, it took to start simulating the models. So taking the formula, building, at that time it was MATLAB, which was terrible. Now it's R or Python script, and then manipulate all the values. And then I get a much better understanding. And then I can go back to the formula and start understanding it better. And that's the same way that I use to sort of create that overview of formulas that all reduce to some sort of update, as I would take the Kalman filter and then simulate the shit out of it because I didn't understand it. And then I started realizing that in certain parameters were in certain ways, it would resemble very much a reinforcement learning algorithm with a high learning rate. And that sort of gave me the basic understanding that I could use to go back and reduce the formula from the one to the other, right? So it's not something that you're supposed or even expected to, can. I'm just going to show you some of these reconceptualizations, some of these simulations, so that you can develop the intuition. And maybe some of you are already in front of me. That would be absolutely expected. But it's not something that people are born with, right? It's just a question of practice. Good. So now we created our basic stupid agents, right? They're not that stupid, actually. Sometimes very complex models are indistinguishable from these noisy models because they're trying to do too many things at the same time. So if you take the hierarchical Gaussian filter or the K theory of mind models with 6 layers, it's basically random behavior, right? But now we're going to try, so they're always useful as null models. But now what we're going to do is we're trying to implement some of the cognitive constraints. And I'm going to make these go away. Yes. So for instance, we could add memory, right? And we discussed that. So we can do that by doing cumulative average. We can do it by moving average. We can do it by optimal Bayesian update. We can do it by weighted Bayesian update. Do you have an intuition of what weighted Bayesian update is? Have you met it before? Yes?
No. No, but my intuition would be that sort of stronger data points require bigger shifts in the prior. If it's a massive change in expectation,
What do you mean by stronger data points?
something that conflicts more with my prior.
Okay, but that's optimal Bayesian update. So what optimal Bayesian update it says, given the priors and the state of the evidence so far, I'm going to automatically adjust the update according to uncertainty and distance between prior and likelihood. The weighted Bayesian updates is a model that actually puts a weight on prior and likelihood. So that you might have a model that even if it would be optimal to update more because the signal is very reliable, right, has a stronger weight on the prior. So it updates it less than optimal. And why would we do that if optimal is optimal? And again, we'll discuss it when we do Bayesian models of cognition, but it's because sometimes we have longer term experiences that shape the way that we integrate our prior and likelihood. Think about, people suffering from psychosis. They might develop coping strategies for which their prior of what is normal in the world as to always overweight the input from the senses because they know they might be having hallucinations, right? Or, if you live in a trustworthy society, right, you might have a higher prior on information that comes from other people, because if other people keep telling you stuff, you might sort of say, well, then maybe I might be wrong. But if you're in a very competitive, cutthroat business environment, right, then you might have a bigger prior on yourself because people might be trying to deceive you. Yes, Martin?
Different from having a much stronger prior.
It's so what you're saying is how different it is. Well, first of all, you cannot really do that for the likelihood, right? So you cannot really concentrate the probability of the likelihood beyond what the data is telling you unless you put a specific parameter there. You could do it for the prior, you're right. But if you want to do it in a systematic way, and as we'll see, if you want to do it in a way that takes into account multiple sources of information, so your sight and your hearing and your prior, or your sight and what Martin is telling you, right? And your prior, then you need to be able to systematically change the weights in a way that is not just about the uncertainty in the distribution.
This could be used for like modeling overconfidence in a sense.
That could be, yes. Yeah. Or underconfidence. Or the development of reputation in your advisors, right? So where you learn how reliable the signal is in the different advisors, and then you differentially adjust the weight that their input gets. Good. We could use reinforcement learning, which I anticipated before, so I'm not going to go through that again. And then, right, does it make sense to add errors? We discussed it a bit last week. But how would you go at thinking, let's say, take even the simple agent that we developed so far, the biased agent or random agent, how would you add an error possibility in that agent? That agent might not do what, well, now I'm giving it a bit away, but the agent should make a certain decision based on the internal mechanism, but a different decision comes out, right? You want to push right, but you push left by mistake. Yeah. Yes?
You're fishing for the softmax.
Yes, so you can put more complex, instead of the sampling from a binomial, you use a softmax for going from rate to the decision, and that has a parameter which is the temperature or inverse temperature according to the formulation. Good. So here I've done it in an even simpler way at this stage. When we get to reinforcement learning, we'll use the softmax. But actually, it's just to reflect what the process might be going on. We have a random agent noise function, which takes as input a rate and a noise. And then it picks a choice given to the sampling of the binomial, but then it samples from a binomial with a rate equal to noise. Right? So if noise is 0.1, there's a 10% chance of making an error. And if that samples 1, so if we're in that 10%, if you want, it just samples a choice from a totally random binomial. Does that make sense? And that, it says, oh, you get distracted while you're filling the task, and then you push something at random. Or, your finger goes down, and it could go down in both directions, right? It could still, even if you made an error, it could still go down to the right choice according to your internal estimation, but it's a different process. And hopefully we'll discuss also how to model that when we'll get to mixture models, but how to infer that at a later stage. So if we have these functions, right, in the interest of keeping our coding simple, how would we reproduce the old agent within this function? It's not a trick question. Yes, Martin? Exactly, right? Which means that we can simply use this function throughout the whole thing, right? No matter whether there's noise or not. And that means it's a good function. Okay, we implement noise. We create a new data set, table. And then what we do is we add an external loop to the previous loop. Right? So we're saying for noise in the sequence from 0 to 0.5 in steps of 0.1. Because, well, we could put higher noise, but if we do have a noise that is above 0.5, then it's kind of a crap task that we've picked, right? Or we need to do something to the participants. Red Bulls to all the participants. And then with that given level of noise, we loop through all the rates. For that given level of rate and noise, we loop through the trials. And then we save. So it's the same logic as before. Right. Then we calculate the cumulative rate. And then we plot, just like before, with the trial as the x, the cumulative rate as the y. The color is given by the rate. And then we make different facets according to the level of noise. Okay, so this very first plot is the one that we were seeing before. Somebody's having more fun than me. As we increase the noise, this is what happens. Take a few seconds. Think about what's going on there. Right. And of course, these again, I'm not doing the 1,000 agents. I'm only doing one agent per each of the rates, per each of the noise, but you should be able to see some trend. And I know Martin knows, but I'm waiting for somebody new. Well, not as new, but yes, you?
So they're all approaching the middle, right?
Yes.
Because they're all kind of being mixed with the middle model, which is like the 50% the rate, right?
Yes.
Because the noise is just that rate.
Yes, exactly.
Yeah.
So since we have a mixture of two binomials, one that has a rate of, let's say, 0.9, and one that has a rate of 0.3, the combination of those two binomials is a process that looks as if it has a rate of 0.7 or something like that, right? It drags it towards the middle. That's one thing. What about the discriminability of the lines? Because we might have that they just shrunk towards the middle, but they keep their ranking. Right? Or we might have that they get shrunk towards the middle and they also get more overlapping and shifting in the ranking. What do you see there? Yes.
The ranking is still going to stabilize, but it takes longer now. So it's
Yes. Good. So basically it's saying in presence of noise, you need more data. And that's also an important lesson because when we run, let's say, have you run power analysis? Method 3, I guess? Not really. Well, one of the things that we will do is we will simulate data from the models to see whether with different experimental design choices, for instance, how many trials or how many participants, we can reconstruct the correct values for the model. And if we assume that the behavior of the participant has no noise, we will assume discriminability that at a fixed amount of trials, that's very different from what is happening in reality if there is noise in the choices. Sometimes you can intervene on the participants to make sure that there's fewer errors, right? So in some studies that we're running on prolific, right, we put regular attention checks, and if you don't pass all the attention checks, you don't get paid. That tends to, well, I would like to say make people more attentive, but actually we create a selection bias, but screening out a certain amount of participants. Or you can change the instructions. You can put somebody close to the participants. If you're working with clinical patients, as it happened to me at a certain point, you make sure they have some food because sometimes they forget to eat and so on and so forth. Yes?
I can't really tell from this plot, but I like the more extreme values of the rate.
Yes?
Are they more affected by the noise than the middle ones?
Yes, they are. Yeah. Because if you're at 0.7, there's already a lot of noise. If you're at 0.9, you're pretty deterministic. So adding noise, it really shifts you. Right? And probability space is not a homogeneous space. I always like to think of it in terms of log odds, where these part get stretched a lot, meaning that you can work in one direction and not really gain that much, right? So if people are accurate 90% of the time, it takes a lot to make them become more accurate. It takes big interventions. If you have a bunch of participants that are really a chance, it doesn't take that much to get them better than that, right? So the same amount of work will push them. Yeah. And now we're talking about the opposite direction, right? So it's very easy to break somebody who has a high performance, but somebody who's ready almost a chance, you can't really break that performance. Does that make sense? Good. Oh yeah, one thing that I wanted to mention is that often we want to remove the noise as much as possible, but sometimes we need to take it into account because we are planning to run things on existing data or on participants who are noisy. And sometimes we even want to add noise. This is something that happens a lot in stuff like sensitive questionnaires, where we ask participants about political, religious, sexual attitudes, where some of these data, people wouldn't want them to be published. And so one of the ways that has come out to ensure privacy on these issues is that at random, some of these questions either get a scrambled answer, or more often, actually, the participant gets a question like, where is the triangle? Right? Left, right, or center. And that doesn't get recorded in the data set. which means that we're giving plausible deniability to the participants about their answers, because it might have been one of the random answers. And we're adding noise to the data, which means we need to change our models to deal with that noise. So noise can also be your friend. Shiny app, let's see. I got a bit excited the other day when doing the Shiny apps, so now you're gonna get to see them. No, sorry. And again, here we can see the variance, which is not very well. Let's see, 1, and we take 0. Actually, let's see, 0 and 1. And we put these at 6. 6, right? We can see that if we have a lot of agents, then it doesn't really make a difference in terms of variance for the noise level. But if we have agents that are more certain, as you were saying, the effect is different, right? Okay. Yes. Okay, now the easy part is done. So what about a responsive agent? We've planned agents that are only acting according to an internal rule. But we can try to formalize the win, stay, lose, shift kind of model, because that takes the loop, makes the loop necessary, because on a trial by trial level, the agent is responding to its environment. And so we're creating a function which at this stage has 2 inputs. One is the own previous choice, and the other one is feedback. It could also be the opponent's previous choice. As I said, as long as you have 2 of the 3, you have everything. Because this reflects exactly the win stay. So if feedback is win, then I'll replicate the previous choice. If feedback is lose, then I'll change the previous choice. Does that make sense? So this is exactly what it's doing. If feedback is equal 1, then choice is equal to previous choice. Else, if feedback is equal to 0, then the choice is 1 minus the previous choice, which is a silly mathematical trick not to have to do a complex loop or if check that says if previous choice was 1, pick 0. If previous choice was 0, pick 1. Because 1 minus previous choice gives us 0 if the previous choice was 1, gives us 1 if the previous choice was 0. Right? There's plenty of these elegant mathematical tricks which make your code much more performing and readable. Then we take the choice and we return it. So if I give to the win, stay, lose, shift agent a previous choice of 1 and a feedback of 0, what's the outcome? Somebody new? Yes?
0.
Yes, because we changed the choice, right? We lost, we changed the choice. Great. So we set up the sequence. We played against a random agent to start with a rate of 0.7 because I had to start somewhere. We say that the self choices are a vector of length trial with an A's inside. The other choices are a vector of length trials with NA as value. We initialize the first. So the win, stay, lose, shift at start doesn't have an input to work. Right? So we just assume that they pick at random. And then we go through a sequence of trials where we pick the other choice according to the random agent or random agent noise I should have put with a rate of whatever we defined. And then for trials above 1, I in 2 to the total amount of trials, we say that if at I minus 1, so in the previous trial, if the choice of self was equal to the choice of other, so if I guessed, then the feedback is 1. Otherwise, the feedback is 0. And the choice of self at this turn is defined by the function of the Win-Staley shift agent with the previous choice of self, self I minus 1, and the feedback. And then we visualize it as before, but we use 2 colors, one for the biased random opponent, which is in blue, and one for the Win-Staley shift agent, which is in red. And if you squint very hard, you can see that the red is basically following one step after the biased agent, which is what we expected to do, right? What we programmed it to do. And here was just the code, right? Creating the table and the ggplot. So I messed up the animation. How about performance? Right. We calculate the cumulative rate for self and the cumulative rate for other. Basically, they're the mirror of each other because the feedback tells us the points that the Win-Staley shift agent is getting. And so 1 minus that tells us the points that the biased agent is getting, right? Because it's a zero-sum game. If one wins, the other loses. We do the plot, and indeed, we actually see that it's nicely mirrored. Again, we see that at the beginning, the performance oscillates a lot, but already from trial 30 or so, it tends to stabilize. Does that make sense? Why does it stabilize? Because it's cumulative performance, right? So we are seeing that even if the biased agent is sometimes shifting, right? A bit at random. Here we get that we know it only shifts a certain amount of times. If it's 0.7, it's mostly likely to stay to the right. And so that level of performance sort of stabilizes. We can change the rate of the biased agent and see how the performance of the Win-Staley shift agent changes. And what you can see is that if the agent is truly random, Win-Staley shift has a perfectly chance performance because there's no way of predicting whether the other is going to stay because it's just purely random. But as the rate increases, meaning as the propensity to pick right increases, there is higher and higher chances that the random agent is going to stay sometimes on the right. And every time that they stay, the Win-Staley shift can exploit that. So the higher it is, the less random the biased agent is, the more the Win-Staley shift is winning. And again, at these level of models, we can think through these things just from the formulas. But as we get to more complex models, that's not going to be the case. So what if we get the model to play against a Win-Staley shift? So again, we create a self and other vectors of choices, and we initialize both of them at random because they're both win-stay-lose shifts. So in the first trial, they don't know what to do. Right? Then we loop through all the trials from the second, and we say that if the previous choices were the same, feedback is equal 1, otherwise feedback is equal 0. And then our reference agent is going to use their previous choice and the feedback, and the other agent is going to use their other previous choice and 1 minus feedback. Again, because if the reference agent won, they lost, and vice versa. We make a table with all that data, self, other, trial, feedback. We do our ggplot, and then I'm putting the previous plot on the left and the new plot on the right. And I guess you can see the difference between the two. Right? Here we had a lot of noise because the random agent was moving up and down at random, and the win-stay-lose shift was sort of rushing after it. While here we have a perfectly deterministic, perfectly mirrored behavior. And we can see that also in the performance, right? Is it kind of art, right? And you can see here that it's perfectly mirror, perfectly regular, and it goes towards 0.5. Okay, so again, these are simple models, but these kind of visualizations are really, really useful. So when we were working on the K-TOM models, trying to understand whether higher level of K-TOM were actually useful given the uncertainty that more parameter introduce, was actually pretty useful even at this level. Right? We could see that any K above 3, so any model that had more than 3 levels of recursion, was getting so uncertain that basically became a noisy model, a biased model. And that was very useful to know as a principal thing. What about cognitive constraints? So memory and errors. What we can do is we can add errors, to the win-stay-lose shift exactly as before, right? We add a noise parameter, and then we just add an if-else check that is not as elegant as the softmax, but it reproduced the idea that you could be just randomly going right or left because you got distracted or whatever. And we plot it. And you can see that we suddenly lose the perfect mirroring. And, well, we still have the mirroring on performance, but the perfect convergence. Because noise is sort of, especially in these short-term memory models that go all in, the win-stay-lose shift, if you haven't gotten the intuition yet, is basically a reinforcement learning model with a learning rate of 1. Right? It just goes all the way in. And this noise is really messing these short-term dependencies in the data that it can use to win some points. Okay, next step is that we want to scale this up to 100 agents. So how do you scale this stuff up to 100? Because now we're looking at 1 win-stay-lose shift against 1 win-stay-lose shift. But, well, but as soon as we add any probabilistic element like the noise, 1 agent is not going to tell us the full picture. Right? So how do we simulate 100, 1,000, 10,000 agents playing against each other from a purely programmatic perspective? Yes? We do a for loop, or as we will see in a follow-up slide, we can create a function that runs whatever we want to run, and then we can parallelize it across cores. So, oh yeah, this is actually, I'm going to take it when we do multi-level models. So option 1 is loop through 100 pairs of agents. And option 2 is to make a function that simulates as and saves a combination of one pair of agents and then parallelize using FIR. That's all in the course notes. But just before coming here and teach, I decided I want to show it to you. And it's perfect because I have still 12 minutes. So have you ever parallelized stuff? That's going to be very useful when we get to stand models, because a stand model can take, at the beginning, it might take 30 minutes to run, which means that if you're running 1,000 simulation, that's 500 hours. But if you, well, we're not gonna actually, we're going to run models that take a few minutes to start with. But if you can parallelize it even on 4 different cores, that's going to make a huge difference for your thing. So what I'm going to use is a package called FIR. FIR, it's 3 R's. FIR. Yes. Which is very smart because it really simplified my parallelization code. I think there's a new, smarter solution which I haven't tried to include yet, but this is very neat because what we do is we load the function. We identify the number of cores that we want to use. The tagged cores. I usually subtract 2 from that number because one of the cores is used by the OS, the operative system, and I usually do other stuff when I run simulations. So I want to have another free core for whatever I'm doing. And then we tell it that we're planning a multi-session, so where we're sending things to multiple cores, and the number of workers is the n of cores. Then we define a function that we want to parallelize. Right? It's called, in this case, simulate population. It takes an agent ID, the number of trials, and the rate. Okay, here I think I should have also put noise. I forgot. See, doing things just before teaching. Then we have that the results are given by run a simulation with an n of trials equal to trials. Agent strategy is win, stay, lose, shift. The agent parameters as a list of noise of equals 0. The opponent strategy is random, and the opponent parameters as the rate equal rate and the noise equals 0. So basically, I'm telling it all the parameters that could vary. And then that what is the agent ID is simply the number of the agent ID, and the opponent rate in these results is that parameter. So I'm saving all the parameters. I'll fix the slide and put things in the right order. And then we say that we want 120 trials, 100 agents, an opponent rate of 0.8 or whatever. We could also make it a vector. And then we feed to a function called future map data frame, because I want the results as data frames. You could put other stuff for 1, 2 agents. So I want to run 100 parallel, or 100 different instances, and them to be parallelized as much as possible. The function to run should be simulate population, where we're giving the previous parameter as an input, the trials and the opponent rate. And then I'm just going to say that it should use the seed that's in the script so it can be reproducible. And that automatically is going to take the function simulate population and run it parallelly along the number of workers that we have available. Again, in this case, it's not going to make any difference, really, given the computers there are today. But even from next week, when we're going to start running some stand models that might take 30 seconds or a minute, it's going to make a huge difference. Okay. For the class that we're going to do tomorrow, I want each of you or each group, according to how you prefer to work, describe 2 strategies, formalize them in code, set them to play against random agent and against win, stay, lose, shift agent, or against each other. 120 trials, 100 agents. Visualize and comment the simulation. And you can really go crazy with your ideas, implement whatever. But if you have no ideas, always happens, you can try to take some inspiration from these slides. For instance, you could say, oh, let's take win, stay, lose, shift. But instead of making it deterministic, I'm going to say that there is a certain percentage of staying when winning and a certain rate of shifting when losing, right? Because then it becomes more interesting for you also to explore. Or you could put different models of memory, right? There's the moving window, there's the reinforcement learning. Some people have implemented the Kalman filter, but I'll urge you to wait with the Kalman filter. It's a bit more complex. We'll get there in time. But whatever you want to do, just the forward simulation, right? Whatever we've done today, you should do that in your GitHub repository and then write a short report that tells which strategies you've picked, describes the strategies, and reports the key plots and what you learned from them, right? Yes?
When is the deadline for this?
I wrote it. I have to add it still to the assignments in the Brightspace, but it's basically by next Thursday.
Next Thursday.
Yeah. So the idea is you should submit it before the next lecture when we start the new thing.
Yeah.
And then I don't know what my how prompt I am in sending feedback, but usually it takes about a week. Depending on how many groups there are, if there are relatively few groups, I tend to send feedback to all the groups. If there's very many groups and individuals, I tend to have the key points highlighted during the next class after I finish going through them. Are there questions? Yes. Yes, I uploaded them and then I didn't put the link, I think. Yes, sorry. Yes, I'll do that, of course. Let me see if I had. Okay, yeah, I'll just do the last slide, and it's next week we'll actually work on reinforcement learning, and we'll start opening up STAN and discuss parameter recovery. Right. So once we have the model, what does the data tell? So we decide a model. We decide that in these specific universe, for our analysis, the only possible mechanisms that participants might have been using are biased agent and win, stay, lose, shift, or reinforcement learning. We decide that. And then once we decide that, what does the data tell us about the parameter values, the propensity to stay when winning, the bias in picking right or left, and so on and so forth. We'll do at a later lecture also, given that we have this universe of models, still the ones we picked, which one is most likely to be true if these are the only possibilities in the universe. Model comparison. Cool. Are there questions? How was the pace? Good. Also have a look at the course materials because there's a few more comments on the code and these sort of things. But with this, thank you for today, and I'll see you tomorrow at 8. Woohoo!